small, very intimate audience. This is going to be about a recording, obviously. Yeah, do you guys have a little bit of background with Layer 7 or not?
A lot.
A lot? You do as well? Yeah? Yeah, okay. So I thought it would help just to introduce us. Layer 7, we've been kind of like an API gateway. Started 22 years ago. It's always been about access control, so we kind of like continue down with API security.
Firewall, XML firewall?
Yeah, XML firewall, but it was always about, like in the early XML firewall days, it was about implementing web server security and stuff like that. So it was always about access control for your APIs in a box. Don't let your developers develop security, do it in a consistent way in that gateway, and over the years, a bunch of customers adopted that and built a bunch of APIs on top of it, right? It's the security aspect of it, it's putting things together, actually exposing an API. So that's what Layer 7 is. I'm Francois, I'm in the engineering side of it, and I'm gonna talk about post-quantum API security. And even if you're not involved in Layer 7, this is gonna be relevant. This is not all a product pitch or anything like that. It's very applicable whether or not you're using Layer 7. And just the other thing I want to mention here is that there's a lot of terminology out there. And then when I first submitted this presentation proposal a few months ago, post-quantum API security, preparing your APIs for Q-Day, it became apparent that actually maybe a better term than post-quantum should be quantum resistance. And maybe instead of saying Q-Day, we should say Y2Q. And that's not us coming up with new words. These are just terminologies that are used out there. I just want to put them side by side because if you're reading additional literature on quantum computer, post-quantum crypto and stuff like that, you will see those. And just so you know, they mean the same thing, right? Post-quantum, quantum resistance, and Q-Day or Y2Q as an analogy to Y2K, right? So a disclaimer slide. We might not deliver something. This is not about a product pitch anyway, so it's not super applicable. Don't take any of this as basically a commitment to release something at a specific time. So post-quantum API security, I broke down the presentation in these 4 chapters. So first we're going to talk about the quantum threat, what it is, and what the solution is. The solution's already exists, right? We're going to talk about what's API specific about it. So what is the API specific exposure to post-quantum API post-quantum cryptography? When is Q-Day or Y2Q, and how do you get prepared for it? And then finally, the research project that we started on our side at Layer 7 in order to ourselves prepare for that and help our customers prepare for them. So I'll start with the quantum threat and its solution. So I'm sure that everybody in this room has a basic understanding of security, right? So you know that our digital world relies on secure communications, privacy of data at rest, right? There's a lot of things involved: authentication, authorization, things like encryption and signatures that give us integrity and trust. And at the foundation of all of this is public key cryptography or asymmetrical crypto. And we use the other kind of crypto a lot today as well, symmetric crypto. But at the basis of symmetric crypto, typically, you need to exchange a key, right? And when you exchange a key at the beginning, there's asymmetric crypto involved most of the time. So what that means is that at the foundation of everything that we do right now from a security perspective is, in particular, these 2 algorithms, RSA and elliptic curve, that are just used about everywhere. And it's great, they're standards, it's working, and it allowed us to develop this digital world that functions really well while maintaining some sense of security. But in the future, after Q-Day, and we'll get into that section later about when that is, and what we mean by Q-Day is when sufficient quantum computing becomes available to a threat actor. that threat actor would be able to use Shor's algorithm and what comes after, right? So this is a new kind of algorithm that is designed to function on a quantum computer, right? So it's very theoretical at the moment. And a sufficiently powerful computer, you can just easily break RSA and elliptic curve. And so basically all of the things that we rely on would become open to leaking and breaches, impersonation, fraud. Everything that we rely on asymmetrical crypto for is kind of broken. And to understand this a little bit better, let's talk about how does that work today? How does crypto keeps us safe, right? If you think about RSA and these other algorithms, you can already break them. You can break RSA right now, right? Breaking RSA is really about factoring a really large number, right? Or breaking a number into its factors. And the larger that starting number, the more work it is for a computer. And the reason that doesn't matter, the reason it's safe is that we are choosing a key size that is large enough that the time to break is so long, so slow that it's just not practical for a real-world attack, right? So you keep that in the hundreds or thousands or even more longer times period, thousands of years, right? And of course, computers, we know, right? They're getting more powerful all the time. That's Moore's law. So as Moore's law does its thing, computers get faster, so they theoretically get better at breaking these factors. So we just increase the key size, right? So in the past, RSA 1024 was a standard. Now, the mostly common use standard is RSA 2048, and the new standard that's being adopted, RSA 4096, is kind of like what's around the corner or what's already starting to be implemented. So that's how crypto is safe right now. But Q-Day represents a big game changer for this established security. And Q-Day, there's two factors that are taking us to Q-Day, two factors that are evolving together. First, there's the compute, right? We have current compute, and in the future, well, we already have quantum computers. They already exist. They're starting to emerge, but they're evolving faster. So the quantum compute is evolving, and the mathematics of it as well. So the quantum algorithms are also themselves evolving. So those are algorithms that are designed to work on quantum computer, taking advantage of this new way of doing computing. So Peter Shor, who now is a professor at MIT, really smart guy, in '95 came up with this new way of thinking, this new mathematics. Hey, if we have a quantum computer, we can use it this way and that way, and it's a new way to do a task, and it allows us to do this factoring much, much more efficiently. So my recommendation is just to keep it at that, right? But if you are a PhD in physics or you're super interested in quantum physics and stuff like that, you can go deeper, and I encourage you to do that, and you will see that, another thing that's changing is we're going from bits to qubits, or we're going from binary gates to quantum gates, linear time versus polynomial time, and something about parallel universe, and to me it sounds like a Marvel movie, so I just like, it's not, you don't need to go there, right? But there are these two things moving forward, and eventually we get to a state where we can say that we've really reach Q-Day from a historical perspective. And so this creates this quantum leap, if you want, where we're leapfrogging Moore's law by centuries, and increasing the key size is no longer having the effect that we are using that for today. So we actually need new mathematics on the cryptography side. This is not quantum, right? This is new crypto math that's going to be needed to protect against these new ways of attacking a system. So the great news is that we already have solutions for this problem. And the beauty of it is you won't need quantum compute to defend against quantum compute, right? you will be able to defend against a quantum cryptographic attack using current computer architecture. You just need new mathematics, new algorithms to replace things like RSA and elliptic curve that are known ahead of time that they're going to be vulnerable to this new technology. So that's what post-quantum crypto, or PQC, is. It's about replacement algorithms for things like RSA and elliptic curve that are known to be quantum resistant, according to today's mathematical knowledge, if you want. And that post-quantum crypto is just something you can run on today's computer, which is awesome. So on August 13 of this year, so just recently, NIST, who is taking the lead on this, just standardized and officialized, if that's a word, 3 standards, and there's a 4th one in the pipeline that's about to come out soon. So MLChem is a key exchange algorithm, and before August 13, these names, these MLChem, MLDSA, SLHDSA, those are names that came out on August 13, but the mathematics of it and that's been existing for a few years already. So I give you the names there, because if you're reading something before August 13, it will be Crystal Kyber and not MLChem. MLDSA, that's a digital signature algorithm. It's also known in the past as crystal dilithiums, which sounds really nerdy to me. And then SLHDSA, yet another digital signature, also known as Sphinx. And the one that's coming down the pipeline is going to be known as FNDSA, which is another digital signature algorithm. And the naming of it before August 13, it was just Falcon. So why do we need these different signature algorithms, right? A digital signature is a digital signature. And so the reason for that is that different digital signature algorithms are optimized for different use cases. So if you think about like creating a signature on one side, I give it to you, you receive it, you validate the signature. So you can optimize the algorithm for how fast you create the signature or how fast you validate it. You can also optimize it for things like how big is the resulting signature, not the key, but the signature that comes out of it. And so that's why these different digital signature algorithms exist. And the secondary reason is that we want to, these are very different from one another. And we also are thinking that in a future where the new Peter Shor comes out, right, of MIT, maybe he's in the Peter Shor's class today and is doing his PhD, and he's coming up with yet another way of thinking about it, which could make, let's say, crystal dilithiums vulnerable in a way that it doesn't look like it from a mathematical perspective right now. We kind of have like these backups that we can rely on. And so by deploying this new infrastructure with the latest crypto standards, we would be in a better position to adapt to that in the future. So that's the solution. And that's awesome. And my presentation would end right there if it wasn't for the fact that even though we're creating the solution, implementing it will be on all of us. It says you, but it's really all of us, right? Because crypto application is all over the place today. Current solutions need to evolve, right? New solutions that you're deploying soon, it will become a requirement. Hey, PQC has to be quantum resistant, so PQC native solutions. The same way that we're talking about cloud native, so maybe in the future we'll talk about PQC native solutions. And yeah, you're going to need to replace, retrofit, and update infrastructure. And when we talk about the quantum readiness, the quantum roadmap, and when exactly Q-Day is going to be, we'll talk more about that. So that's the quantum threat and the solution. Next, we're going to talk about what does this got to do with APIs, right? It's not obvious. So the first thing that I'll say about that is that, and we saw that in the keynote we were talking about In the keynote, there was like some ransomware and a lot of talk about this, right? If you think about it, these really complicated backdoor phishing attacks, and some of them are really complicated, right? At first, a computer gets infected, and there's a whole network of people that, that exists because your front door is locked, right? Like if you did things right, you're implementing API access control, you're checking that you don't have vulnerabilities, you're patching things, and you have sound API security. Your API is your front door, right? So it is locked if you're doing things correctly. But in the future, a crypto attack is kind of like a key to that front door because RSA elliptic curve breaks down. So you can, if an attacker can break your private key, why not just go through the front door? That's the easiest thing, right? And just pull all the data, and it's instant gratification from that perspective for the attacker. So your API is a really serious target. So where are the API security specific vulnerabilities? And in order to take a look at that, I decided to look at it from the perspective of Layer 7's API security reference architecture. And I've got the two sides to this. So on the blue side, on the left side, you've got the runtime API traffic, right? So in this box here, you've got a unit of API security deployment. So your API traffic comes in from the front door. That's some sort of ingress, and then it gets passed to our Layer 7 gateway. And then at runtime, we'll talk to maybe an identity provider to get some claims about an identity and check that something is still valid or it's not revoked, or you'll talk to a state provider because as part of your security rules, you're coordinating things between gateways, right? So you have a connection to state providers, you have a connection obviously to your API backend or in order to service these API transactions. So that's how it works in the Layer 7 reference architecture, and then we have the API security configuration side of it. So if I'm an API owner, I want to publish an API, I probably go to a developer portal in my organization. I deploy an API and I say, I want this API to have these rules attached to it, right? So that's an API security source of truth, that developer portal. And in our architecture, in the deployment, the API security runtime deployment, we have this little ground-to-cloud agent that's responsible for monitoring, for pulling these changes from these sources of truth. And then the ground-to-cloud agent represents that locally as a Kubernetes resource definition, right? So each API, each runtime rule is potentially its own resource definition on the Kubernetes runtime. And then we have our own Kubernetes operator that builds on top of that Kubernetes ecosystem to apply these changes to each of the gateway running in that cluster. So the way it works for us, you might have one dev portal for your APIs. A customer might have, they might manage configuration as code for their API security and store that in maybe a Git repo or maybe multiple Git repos. Yeah, your source of truth that are decoupled from your API runtime. And you might have, one of these on Amazon, on the East Coast, on the West Coast, another one on Azure, another one on premise, right? You can have as many of those as you want, pointing back to the same API security source of truth. Okay, so let's get back to a quantum threat from the perspective of that architecture. And the first exploit that we are going to talk about is if you are thinking about a JWT-based API access control, which is very common for us. JWT is JSON Web Token, if you're not familiar with it. And yeah, how does that work? So if you think about how it works today, this API, right? So that'll be, for example, our gateway, has a relationship, a trust relationship with an identity provider. That identity provider is responsible for authenticating an application or user and issuing a token for the purposes of calling an API, right? So that top line there, that's OpenID Connect or those types of protocol. You get a token, and the gateway is trusting that IDP via this JWK, which is the JSON Web Key, which is what's used to sign the token. And so what happens is that the application presents that token back to the runtime and says, hey, I've got this token, and this is who I am, and this token, IIT, is it's valid until, right, or issued at. There's lots of claims that are included in that token, which is used at runtime by the API gateway to decide whether or not something should be allowed, and maybe to restrict the data that comes out based on those claims. And the API gateway just trusts the JOT, trusts the token, it trusts the claims that are embedded inside of it because it has a trust relationship. It says, oh, this was indeed signed. There's a digital signature that seems to be coming from the private key associated with that JWK that I'm configured to trust. So that's awesome, right? That's how it works today. It's very sound. But in a post-quantum world, a quantum attacker would basically get the same JWK. It's public, right? It's like a digital certificate. It's the public side of it. And then using that, you can apply that new mathematics using the quantum computer, and you can find a factor, therefore you can get the private key associated with it. And once you have the private key, you can do everything that the IDP can do. So you can forge your own tokens, you can claim any identity, you can claim any permissions that otherwise would have been decided by the identity provider. You can set any expiration you want, and you can create as many of those as you want, as fast as you want, whenever you want, and the API gateway would not be able to distinguish those, right? So the forged token would have a signature that is using the same private key as the IDP. So that would allow you to call an API that you should not be allowed to call, or to call an API in a way that has fewer restrictions that you otherwise would have, because it allows you to bypass all the authentication time policies that are enforced on the IDP, which is probably what Vadim is talking about in the room next door. So what you need to protect against this future exploit is a post-quantum JOT, or a quantum-resistant JOT. So to counter this threat, the token issuer needs to switch to PQC standards. So, and the token issuer needs to be able to sign those tokens using those new standards. The resource server, which often is our gateway, needs to be able to validate those signatures. So it also needs that new library on its side. But before all this can happen, you also need to evolve the standard, right? JSON Web Token JOT says that you can have a signature in there. That signature is standardized by another standard called JWS, JSON Web Signature. And JSON Web Signature is one of the standards that points to JWA, which is another standard. And here you can see section 3.1 of the standard, and you can see this is symmetrical, but RSA. RSA, elliptic curve. This is baked into the standard. So if you have a standard-based JOT, you can't do that right now with PQC algorithm, because the standard itself needs to evolve. And we're going to get back to this when we talk about our research project, because that's the first thing we decide to look at in our lab for layer 7. So another use case is protecting the API security control plane. So remember that architecture, there's the runtime, and then there's the control plane, right? So imagine that on your API security runtime, you're PQC ready. You went through all the changes, you tested it, it's working, it's awesome. But maybe on one of the sources of truth, you're lagging behind, right? Maybe a portal or somewhere where you're storing this information is not quite there yet. You're really only as strong as your weakest point. And the point I want to make here is that PQC remediation needs to be all-encompassing. You can't, fix it only in one place. And I'll illustrate what I mean by that. And so our same attacker realized that, maybe they're using JOT tokens there that are post-quantum crypto. They're using HTTPS TLS 1.6 or whatever it's going to be in the future that implements that. It's all good. Oh, but look, there's this API security source of truth. That's not quite ready. So I'm going to like inject my own little, maybe another security policy that's a special case. If user equals me, just bypass all these things, whatever it is, right? So you can inject something into the system. Our ground to cloud agent is going to pick it up, and our operator is going to apply it, and it makes its way into the runtime. And so now, after altering this API security rules, you would be able to attack the API like this, right? So you can now leverage that new cheat to break into the API. Even that front door is, fully PQC ready. So it's not fair, but it needs to be all-encompassing, and so you're only as strong as your weakest point in there. How am I doing for time? Good? Okay, I'm about halfway, I think. So let's talk about when Q-Day is. Q-Day or Y2Q. Y2Q is analogous to Y2K, right? I think I'm definitely old enough to remember Y2K, right? I was still a student, I guess, at the time. But the big difference is that Y2K had a very specific time. It's January 1st, 2000. You see it coming, right? It's not Q-Day itself. That is definitely more of a question mark. And hopefully the closer we get to Q-Day, the clearer we are when it's coming. But it is a bit of a moving target right now. And remember how I was talking about Q-Day is this two factors working side by side that takes us there. Here are these two factors. There's the quantum compute on the left side and the quantum algorithms on the right side. So on the quantum computer side, this is something I got from Statistica, and I did some additional research here and extrapolate from there based on what we saw happening after that. But yeah, as early as 1998, there was a quantum computer in the world, right? So that's a long time ago. It's not that new, but it's a really, it's starting slow and it's evolving faster, right? So if you fast forward 2019, a few years ago, 53 qubits. 2022, IBM came out with Osprey, 433 qubits. And the year after, last year, IBM came out with Condor, 1,100 qubits. So things are moving fast at that level. And if we see a similar curve as we saw for non-quantum compute evolution, you can expect things to be accelerating from this point. So maybe in 2030 something, we are reaching 1 million qubits. So the quantum compute itself is getting more sophisticated, and the mathematics of it, starting with in 1994, Peter Shor, is also evolving, right? So there are some clever mathematicians that are, finding new ways to finding the factors of prime number, and they come up with optimizations and truncation techniques. And so if you read this article, it's basically building on top of this, because it's still very new, right? The quantum computers are barely available yet, so it's still being defined. But you can see the solve time to crack an RSA 2048, and you can see that depending on how big the computer you're using, it's getting more efficient. So the compute is going to get stronger, and while this is happening, the amount of compute that you're going to need to break RSA is also going to go down. So eventually, we reach that Q-Day. So when exactly is Q-Day? I don't know, 2030 something, maybe. All right, spicy plot twist: harvest now, decrypt later. Another way to think about how things work today is privacy, right? So you've got an app calling an API over a secure channel. An eavesdropper, being able to see that traffic would not be able to decrypt its content. It would be useless because it's encrypted. And what does it mean to eavesdrop? Like, what do you mean eavesdrop? Like, you can't eavesdrop on my traffic. Well, there actually have been instances of, foreign nation actors that are actually able to reroute internet traffic in order to mine. This is a thing. People are legitimately concerned about this. But it's okay, because it's encrypted, right? So that's today. But harvest now, decrypt later, the idea is that you would capture today the content that's encrypted, and in the future, when quantum computers are available, you can just decrypt it later. So that's harvest now, decrypt later. Now, why does that matter? So based on that, I'm going to define something, the secure for period. So the secure for period is the length of time for a secret embedded in your API to remain secret. So let's say you've got a nuclear code reset API. That's a goofy example, but just to illustrate, right? And I have like a procedure in place. This automatically resets every 3 months. There's a new nuclear code that's set on the system. So the secure for period for that is 3 months. Because if I can harvest that traffic now where the new code was set, let's say, I have 3 months until it's reset. So if I get a quantum computer in the next 3 months, I can reset the nuclear code. Otherwise, it's too late. Whereas another example, retrieve a health record. You get a health system API, and there's information coming back that's private, right? I don't want people to know that I have this weird medical thing. I'm not going to tell you what it is, right? So to me, this information has to be secure for infinite. And as a matter of fact, this is what we have seen over years. In some cases, you see some healthcare authorities that are really pushing back on the concept of exposing on the public side a secure system like an API where that information is available. Because people are concerned about the future prospect of somebody being able to harvest now and decrypt later that information. So the longer the secure for period, the higher the security risk. The secure for period, if a customer asks layer 7, what is the secure for period of my API? I don't know. It's very application specific, right? It's very domain specific. It really is about what your API is doing and what is the information going through it. The secure for period is also sometimes dictated by business rules or policies or regulations that are going to say, well, customer information needs to be kept secure for a certain amount of time, or there are a number of different factors that come into what is your secure for period. And so yeah, look at your API for instances of secure for content. So that's the secure for period. And the second thing we're going to look at is time to retrofit. So some of the most critical targets tend to be large organizations, right? Think about the electric grid, or think about something that is potentially government-managed infrastructure or very large corporations, and those same organizations, the really large ones, sometimes we see it from past experience, they can be slow to adapt. And on top of it, they tend to have more complex environments, which adds to the work. So some environments are really complex, multi-layered architectures, things that have been started, decades ago, and they build on top of each other, and like every year, like new layers that come in. So, it adds complexity to the task of retrofitting post-quantum crypto. And you can't flick the switch on all systems at once. Obviously, that'd be crazy. So therefore, you need a period of overlapping support between the PQC standards and the pre-QC standards. And so these needs to run in parallel for a certain amount of time. It adds to the scope. It adds to the complexity. And so what is the time to retrofit? It's going to be different for everybody. But in some cases, we're talking about years, many years. All right, let's talk about the timeline. So when do you need to start looking at that? Oh, what's going on here? Oh, something didn't render here because I missed that, but here should say Q day. So this is Q day, and we're working backwards from there. And working backward, and we start looking at the secure for period. So what is your secure for period? For some API, it's going to be 0, right? For some API, it's going to be months or whatever, years. So let's take you there. And then how long does it take you to remediate, to retrofit everything is the total remediation duration. So if you work backwards from there and you get here, this is when you're starting. So yeah, let's put some actual dates on that. Well, before we do that, let's talk about establishing a quantum readiness roadmap. So there are already some great assets that have been published on that topic. In particular, NIST, CISA, and NSA published something called Quantum Readiness Migration to Post-Quantum Crypto. It's a public asset that's meant to be a reference for people looking at that. If you're in Europe, IETF is also very relevant. But yeah, what do you need to do as part of that roadmap? You should prepare a crypto inventory. Where and how is crypto used in your organization? Look for what are your secure for factors. Try to quantify those, because that's very relevant to your roadmap. Where are the blockers, if any? Is there something in your architecture that's not going to be able to adapt, right? And then high-level scope the migration, just so you get an idea, like are we talking about 2 weeks or are we talking about 20 years? That's really important. And then you should prioritize those in most likely or most damaging target and start estimating your time to retrofit and discuss with technology providers, right? You should demand crypto agility for your system providers, such as ourselves. And you should look for quantum resistance in roadmaps, right? You might decide that you need to start that in 2026, and maybe you're talking to a product manager and it's like, no, quantum crypto is too far down the road. It's not on our roadmap right now, and their roadmap goes to 2027. You might have a problem, and you might want to insist on that based on your estimate of where you need to go. All right, back to the roadmap and actual dates. Just for fun here, I'm putting a few guesses here. Like I said, it feels like 2030 something right now, but it's kind of like that, right? But what if it is? What if it's 2030, right? Things are moving fast. I actually think that's very plausible. And what if you have a situation where you have a 2-year secure period and it's going to take you 4 years to do your remediation? That takes us to 2024. You're already too late, right? This is a very pessimistic scenario, but you're already too late, right? So it's probably in the middle, right? So a more optimistic scenario, that won't be available until 2035. I don't have a secure period. I mean, it's just days. And I can figure this out in 2 years. It takes you to 2032. Yeah, maybe it is somebody else's problem. True. I wish I could tell you exactly when it is. But yeah, let's talk about the light. So in this last section, I'm going to talk about what we're observing in our development, getting ready for this. So remember what I said about post-quantum JOT. So that's actually what we decided to try as a first use case. And so we had to basically simulate the standard evolving and make some assumptions based on that. We actually implemented the use of the post-quantum algorithms as part of digital signatures. And it works great. So there's a library called Joseph, which is the library where the JOT digital signatures are being handled. And so it's open source. We forked it. We created our own version of it. We added the dilithium algorithms as part of it. Bouncy Castle, which is a Java provider of a crypto implementation, they already have some crypto algorithms in their recent version. So the Bouncy Castle PQC provider has these algorithms in it, so we can start experimenting with them. And yeah, we rebuilt the layer 7 gateway. We added an endpoint for creating tokens, another endpoint for validating tokens, and just make sure that it works. And it does. Works awesome. So checkbox, quantum resistant JOT. Works great. We can look at it. This is, if you're familiar with using JOT tokens, this is a screenshot of jwt.io, which is kind of like an online utility that people use to look what's inside a token. It cannot, validate the signature because jwt.io obviously is not PQC ready itself, but you can still decode it. You can see the dilithium algorithm being listed, and in the header, that would be MLDSA. You can tell that that screenshot was done before August 13. So yeah, it works great. And then we also decided to take a look at, hey, is there going to be a tax involved? Like, because the other thing you need to consider is that when you're making changes like that, maybe API volumes, for some of our customers, that's extremely important, right? They have a layer 7 capacity based on how thousands of API calls they are able to support per second, let's say. So how does that work? Is that going to be a big cost? And remember what I said about the different signature algorithms being optimized for different things? Well, this is really interesting observation we did using MLDSA. We have our two endpoints, encoding and decoding, and then we're comparing that to RSA 2048. So it's actually faster for signing the JOT, which is, I did not expect that. I knew that that it would be optimized for encoding, but I thought it would be faster than the other post-quantum crypto algorithm. But it's actually potentially faster than RSA 2048, which is great news. And the validation, in this case, we were measuring a 10% performance degradation, which is not bad. It's not that big a deal, right, for the validation of those tokens. I say it's not that big a deal because in the runtime processing of an API, the portion of time that you're using to validate a token, for us, that's not typically what the bottleneck is. So yeah, it looks great. And we're continuing down the path of looking at other areas of the product where crypto is being used and making sure that we are ready for all of those. So hey, this is it. This is my last slide. So in conclusion, Layer 7 will be ready. We are here to help you. Again, take a look at these publications around how to create your own quantum readiness roadmap. Prepare a crypto inventory, high-level scope the migration, discuss with your technology providers such as ourselves, and yeah, try to figure out when that is going to be for you. If it's not in 2024, maybe even if it's 2026, you'll need to see it in your budget for 2025 leading into it, right? So expect to see that kind of stuff coming up into your roadmap. Thank you.